Alright, so next we'll have Jalving from Wisconsin, and will be telling us something about graph-based modeling using JuMP.
Thanks, Miles. So, again, my name is Jalving. I'm a PhD student at the University of Wisconsin-Madison in the Department of Chemical and Biological Engineering, working with Professor Victor Zavala. And for this talk, I would like to introduce Plasmo.jl, although that's unofficial. I haven't actually pushed the package to GitHub yet. I'm not totally convinced. I'm pretty close that that's going to be the name of the package. But again, after this presentation, I'm certainly open to ideas for a name that might be more reflective, that might make more sense after the presentation once you really understand what it does. And so before I really dive into specific motivations for a graph-based modeling framework, I think it'd be helpful to just give you the key features of what the package really does, and then maybe by the end it'll kind of make more sense to you what it really is. So Plasmo is an acronym. It stands for Platform for Scalable Modeling and Optimization. The idea here is it's a graph-based modeling framework with the key feature that we have component models that we associate with nodes and edges. The key is nodes and edges, not just nodes. The idea is to facilitate the construction of hierarchical graphs, and to do that, it uses the abstraction of subgraphs. You can have graphs containing graphs. It really focuses on modularity. You have models which are contained within components which communicate with each other, and then we can manipulate this graph structure, which becomes the solver interface, depending on the type of the problem. And again, the idea here is we want it to make it easy to model very complex systems. And so, overview of this presentation, first I'd like to give just a motivation. What are the types of complex systems that our group really is interested in solving? Then I want to show you how to really model those systems with components, specifically using this Plasmo package, give you some of the applications that we've been successful with, and then kind of end on some of the design considerations where I'd like to take the package in the future, and then some of the things I'd like to do this week. So beyond the prominent research theme for our group is systems. That ranges from multi-scale systems, not necessarily this exact system, but for instance a multi-scale system which could cover all the way from a supply chain network to a molecular system. All of these models, all of these systems, individual systems are modeled very efficiently on their own, but of course subsystems inform the decisions made at the higher level systems, and coupling those systems is a non-trivial task. We're also very interested in multistage stochastic programming, so fortunate that you all just got to see multistage stochastic programming in STDP. We're also very interested in that field, especially for energy systems and planning. We're also interested in asynchronous systems, in cases where you might have multiple players that are optimizing on their own and they may or may not be cooperating. Can we have a framework that makes it easy to model something like that? And so physically, the types of problems we deal with are generally infrastructure. We have nonlinear, non-convex optimization problems. Also looking for planning in energy systems, which leads to a lot of stochastic programming within the group. We're also interested in model predictive control, especially as we get into more microgrid type applications, where a microgrid is kind of a mini grid that can disconnect itself from the main power grid and has its own distributed generation without. So that's kind of an overview of some of the problems we look into, but to really give you an idea of the complexity and the scale of these problems, it helps to see a couple of the figures. Again, we're interested in infrastructure networks, and specifically we can have hierarchical networks. So in this case, we might have the electric power and the natural gas networks, which themselves are very complex systems, but they can be connected in various space and time scales, connected in different places and on different levels. We're also interested in looking at technology landscapes. So new technology production is really going towards this multi-scale paradigm where you might have materials which really determine the performance of the devices that they're embedded in, but the device also provides the constraints that you need to design the material to, and that propagates all the way to the systems level, which goes to the infrastructure level, and those infrastructures are also communicating with each other. So the idea here is if you want to invent or develop a new technology, having this kind of platform where you can systematically analyze the performance of the technology with the existing markets and existing options in systems, we would like a very expressive way to actually model that. Of course, that sounds very grandiose, and it's not it's no simple task. There are a lot of challenges. Of course, any multi-scale model is going to have millions of constraints and variables, possibly billions, which is just an intractable optimization problem to begin with. Generally, how you approach that is you apply model reduction techniques at certain levels and then embed those in a reduced form model. Of course, generally that's usually done very ad hoc, and we would like a way to be more systematic about that. A very smart way to govern, how do we reduce these models, how do we partition them, how do we embed them within larger models. Of course, just the number of connections within the models and the systems themselves makes the model instantiation very non-trivial. In the case of stochastic programs, what should my scenarios be, how many scenarios, how do I even really look at the solution to my optimization problem once I solve it when the system is this complicated. Of course, we're also interested in modeling the asynchronicity in large communicating systems, especially in decentralized control applications. Again, we would like to have a framework where we can actually model that asynchronicity. What information are multiple players communicating with each other? Are they cooperating? How often are they exchanging information? And is that information necessarily always exchanged at the same time interval? We would like a way to actually express that. And so, kind of approaching this package, again, my background's in chemical engineering. I had a little bit of experience with the Modelica platform, which is a component-based modeling platform that came out of the mechatronics community in the 90s. It has a strong following, but again, it's very simulation-based. People have designed Optimica and further past that, JModelica, which is more of an optimization interface that sits on top of Modelica. Again, some of the limitations with that was it was designed for simulation. It's limited on what kind of optimization problems it can really solve. For instance, it can't do any sort of mixed integer problem. Also, personally, I always found writing connectors in Modelica to be extremely complicated. I don't know if anyone in the room has really had experience doing that sort of activity. Then there's also GPROMs, which is more ubiquitous in the chemical engineering industry. They do equation-oriented chemical flow sheeting. I really like the way they do their component modeling and connections, but you wouldn't model an infrastructure type problem in GPROMs. It's not meant for problems of that scale. And of course, it's also a commercial tool. And so this got us thinking, we originally when I started, we thought of a lot of different abstractions, but eventually we decided we really just need to revisit the goals and start from the goals. What do we really want? We want the models to be encapsulated. We want some sort of modularity. We want to be able to make component models and reuse them in many places. We want to make it easy to really look at the solution once we have one, or if we don't, can we come up with a strategy based on the component models to get to one? And we're also interested in, how do you really facilitate modeling of communication systems? And that ultimately brought us to graphs. Not graphs in the sense of computationally trying to solve the problem, but a graph in the sense of it actually lends itself very well to actually modeling a very complex problem. So in this case, in our multi-scale system, we really can think of a supply chain as a graph containing nodes, which themselves are subgraphs, and that goes down all the way to the granularity that the modeler really wishes to achieve. So it kind of helps to really see the abstractions, the graph abstractions that really apply to the Plasmo.jl package. So assume everyone in the room is really familiar with graph theory. When I started on this, I didn't actually know what graph theory was, coming from chemical engineering. So it turned out it was a really, this was kind of an aha moment. It's like, oh, this is the abstraction that will work for doing these hierarchical systems. So of course we have a graph, which is a collection of vertices, I call nodes and edges. And then the other piece is, in this case, we see A is a subgraph of B. But we can also think that we have the 3 red nodes, which have two graphs defined on those nodes. And what we see is that actually makes that actually provides the syntax for coupling systems, and we can always specify which graph we're coupling in when we're looking at the neighbors of a node. So in this case, the nodes are labeled with their degree or the number of neighbors. So in graph A, the red nodes have 1, 2, 1, but in graph B, they're 3, 3, 2. And we could always define different graphs on the same set of nodes and achieve a different type of structure. And so that was the first aha. The second aha was, how do we really associate the modeling with this graph structure? And so in this case, we could think each node could contain its own model, and that model could be as small as a single variable, or it could be as large as a large-scale JuMP model. there's really no restriction on what you can really do with it. And then the other piece was, it was also very important that you need to be able to associate models with the edges as well, and that was very important for network type models, and then also providing logical connections. We wanted to couple large systems. The other piece, of course, here is I call it a coupling function, but you can also just really call it the linking constraint, which is specifically just the type of constraint that's linking the two models together. So again, we have models on the nodes and edges, which are completely encapsulated, and then we just need to provide the linking constraints at in the right levels of the graph that really say how our models connected to each other. And what we found is this really scales to help us model very large systems. And so now that I've managed to really cover a lot of the motivation, again, go back to the key features, and some of these are still in progress. I'm hoping to knock these out really soon. We can, of course, associate models. In this case, up to this point, it's always been JuMP models and linking constraints, which are just typical constraints with the nodes and edges within a graph. We exploit the subgraph abstraction, and this enables developing these hierarchies of the models. Again, we can define multiple graphs on one set of nodes. And again, a node can only have one component model. It uses light graphs as the backend. Originally, when I developed it, I just started writing my own graph backend and then realized it was completely unoptimized and inefficient. So then I actually tried graphs.jl and realized that I was running into a lot of bugs, and that wasn't a very supported package, and it seemed that the whole community was really going towards light graphs. So I went ahead and just wrote a quick interface, and now we use this light graphs as the graph backend, and we use JuMP as the modeling end. So of course, we can also access, when we solve a model, we access the model information on the node or the edge. And then we can also provide, if we have the right structured interface, we can provide that to a parallel solver. So we're also providing a lot of the interfaces to a lot of the parallel solvers, such as PIPs and DSP, which are written from Argon. So the old syntax, so just an example of how this might look for like a really simple problem. So imagine you have a graph with 3 nodes and 2 edges. You can just create a graph or plasma graph. You can add three nodes to that, connect them with the 2 edges. Say I just have some simple model which has some variable x. I can just set the model on those nodes. And then originally how I did this was I provided a coupling function which would take a graph argument, an edge, and then this couple nodes function, which was a function that required a very specific signature. In this case, we could provide a constraint to a model which could use these get connected from and get connected to, which took the graph as an argument. So again, a node is connected to the other nodes within a graph. So as long as you're always providing that graph as an argument, you can always distill it down to the level of granularity that you want to connect at. Although the new syntax is much more, it makes it much more easy to just work directly with JuMP. So I wrote this type, just called a function, just a graph model, and you can add nodes directly to the model, add edges directly to that, set them in the same way, and then just have a macro that does a link constraint where all we do is provide the edge, provide the edge or the node to that link constraint, and then we can use the same graph syntax to access the variables and constraints within the model. And again, we can. Another piece here is, again, we can solve it serially. It's always, you can always pull the flat JuMP model out and solve it, or you can always take the structure and pose it to a parallel solver. And so I'd also like to provide some of the examples. Our group does a lot of infrastructure. So for instance, we use this framework to do some gas networks. So in this case, these gas networks are typically already conveniently formulated as usually networks of nodes and edges. The nodes usually represent gas junctions in the network, and then we can have this set L, which is the set of pipelines, which may or may not have compressors. We have the set S, which would be, you could have gas supplies on the nodes, or we could have gas demands on the nodes. And then we have, again, the pipelines connecting them. So the equations themselves, in this case, I just implemented them in JuMP specifically. So I'd have a JuMP component model that represented my pipeline, and then you could have various different types of models for that. In this case, I just had a pipeline that had the isothermal Euler equations, which is my mass and momentum balances. You can also have very reduced forms. You can always build a topology and then trade out different reduced forms in the models as you see necessary and play with the system to that degree. And of course, we also have our compressor power, our boundary conditions, our node conservation, supply and demand. A lot of these equations comes into looking at them and thinking of how do we really want to express the components. So for instance, node conservation is a constraint that really connects all of the nodes to its neighbors. So to that we thought, well, we can make a node component that is going to have a linking constraint that links it to its neighbors and enforces that conservation. And I'll show you in a figure how that really comes together. So in this case, we have a graph that has 7 nodes and 6 edges and three graphs total. So we think we have one junction system, and we represent that as a graph. Another junction system with just demands. We call that subgraph 2. And then we have this graph of a gas network, which is a graph that contains both of those graphs. And so what we see is, on the left side, that junction in subgraph 1, he has 3 neighbors, and we can write this coupling to his supplies and demands in a very general way. The key is we can write it in a very general way and say, I know my neighbors in and out, so I know what my supplies and demands are, so I can get my total supply and demand. Within the graph of the gas network, we see that he only has one neighbor, and that's another junction. So we can write another generic coupling function and assign that to the same junction and say, my mass in must, I can give the conservation equation saying my mass in and mass out must sum to 0. So I can write the sum to 0 constraint that way. And we also have the pipeline, of course, and we can just provide the boundary conditions with the link constraint on the pipeline directly. And so what we found is this particular abstraction really worked for building up this type of scale of a system. And then it goes even further. So when we got into the power grid modeling, I was able to just develop a graph in the same way in terms of, instead of junctions and supplies and demands and pipelines, I just had power lines, buses, and loads. And then I was able to just couple the gas and the power systems at certain generators and demands. So an example of how that might look would be, I have a graph model. I can always take the graph out of my graph model, and I can directly add subgraphs. So if I had my power network and gas network subgraphs, I could add that directly to the graph. If I knew where my generator was, I could take that, take my demand, add an edge between those, and do a link constraint. And so the key here was, when it came to really doing the coupled problem, it was just a few lines of code, taking my 2 systems, looking at where all the connections were, adding the edges, and saying these are how the 2 systems are linked using link constraints. And so that really worked. We really found that these infrastructure models, specifically, just each one as a graph, can be developed independently, and we can always couple it within a larger system. If you need to introduce, a different level of coupling, you just need to define a new graph, and then you can define the link constraints within that graph. We did an Illinois case study, of course, and found coupling the 2 systems, of course, opens a feasible space, and you can find, in this case, the gas generators act as dispatchable loads to the gas operator. So you get more gas delivered, you get higher revenue. That was compared to the uncoordinated case, which I'll cover probably in 2 slides here, and how we really do that. I also just wanted to mention that we are interested in multistage stochastic programming, and so now that I've introduced all of these graph modeling concepts, the whole idea is this graph abstraction also corresponds to the node-based abstraction for stochastic programming. So in this case, component models would be associated with nodes, which would be scenarios in this case, and the link constraints would propagate transitions from stage to stage. So this really worked for up to 4 or 5 stages, depending on how many scenarios you consider for solving just an extensive form problem. We're also interested, admittedly, in trying to apply STP algorithms to this. In this case, we're kind of working on just developing a custom graph type, which would just be very sparse tree where we're able to associate nodes with stages instead and try to write a generic STP algorithm that just looks at the structure of the tree and applies in a generic form that way. So, of course, we can also make it easy to, for instance, put a gas network within a stochastic programming problem. So instead of having to go in and say I want to turn my problem into a stochastic program and go in and add in all the scenario indices and modify the complete model, the idea here is I can always just instantiate my gas network problem and take that graph model and embed it within nodes themselves and then provide link constraints that represent the stochastic program. So the idea here is you can always just build up a graph, just say, okay, I want the flat model for that, and then embed that within another graph, and then manage the structure that way. And so that really simplified the construction of just adding more and more layers onto the system. And so this is really the end of the talk. Kind of the future direction. I'd like to see if it's possible to generalize the modeling interface. For right now, it strictly uses JuMP, and I think it's probably going to be like that for the time being. I haven't really thought if I really want to consider a more just abstract model just for a node or an edge. I'm also looking for a suitable abstraction for what we call these computational workflows. So before, when I said we had the uncoordinated case with the gas and electric grid, in that case it was really easy because I just had one model for each system, and I was able to solve one and give the information to the other one. But that could get more complicated when you have more systems, especially in a decentralized control case. So I'm thinking of what a proper abstraction would be on top of this physical system. So for instance, you could have another graph sitting on this physical system that represents, what exactly do you actually want to do with that model? And in this case, we might say you might have a virtual node that says, I just want to solve the power system and give the information to the other system. Or I might just have a virtual node that says, just solve the couple problem. So again, we're thinking it's very analogous to a computation graph, although there can be cycles, so we might want to introduce some sort of conditions. Especially when I did it in this system, there was really no guarantee of convergence. It just happened to in that case. That's also really motivating. Can we have generic graph abstractions and then apply these algorithmic strategies? For example, you might have scheduling and operation systems. It kind of follows the same dialogue. And can we just have generic graphs and then have generic algorithms that work on those graphs, which contain models? And we're also looking at, since we have the light graphs back end, I'm thinking of coming up with strategies that do the graph partitioning. And this might be a systematic way to do the model reduction, partition it, reduce the model, and then understand the effects of that model reduction. And of course, we're also interested in different initialization strategies. You might be able to swap in reduced models, solve the problem, take those values, and then swap in a more sophisticated model and actually start with maybe a closer solution. And then maybe way down the road, we're also interested in maybe doing simulation interfaces, just in terms of the gas networks. We were successful in doing some optimization on some very coarse problems, but we could also theoretically solve these optimization problems and then do some sort of simulation verification on the same model. And so for my goals right now, I would really just like to finalize this abstraction, push it to GitHub, and then maybe this week actually figure out a good abstraction for the graph communication. Although now that I've seen the presentation for power models, I would actually like to see maybe how that integrates, and maybe if I could actually use some of the power models components directly within the graph. So that concludes, so I could take questions.
Yeah, I'm thinking sort of more about a simpler problem, but there's a lot of optimization problems from all sorts of domains where there's a large component that is a graph problem, and then there are side constraints, additional complications. So one can imagine developing a graph-based system where you make it easy to develop the graph, and also the constraints that are like clearly graph-based constraints, and then have other parts of the system that capture everything else. Mm-hmm. Are you developing a system where that would be easy to do, to like have the large graph part and then the part that's not graph, and do they just work together in terms of you've got all the constraints?
So if I understand, you have one part that one part represents the graph itself, and the constraints are completely separate from that?
Well, you've got the graph that like might have flow constraints on it, mm-hmm. but then you might have a bunch of constraints that aren't constraints that look like flow constraints. They might be global constraints.
Oh, right.
You might have a budget constraint. You might have lots of things that tie things together more globally.
So the one way I thought to do that is you can always do something like that if you just simply define more nodes and edges. So you can always define another graph that might aggregate a bunch of nodes and say all of you need to satisfy some constraint, or some constraint I put on all of you. That's one way to do it. If you use the graph model object, of course, you can go in and just break the structure of the problem and add a global constraint if you really want to, but then you kind of do lose some of the modularity that way. I think with the current abstraction, that would be something. The way I would go about it is I would actually probably define a new layer of the graph and then create the according nodes and edges and keep the structure that way.
Also, is that a comment that like having something that's a large part that's a graph and a part that's not a graph is pretty common. So forcing it into an entire graph structure is forcing a certain amount of non-natural modeling.
So what would the non-graph part, like specifically, can you say what that might be?
Suppose you've got a limit on total flow,
Mm-hmm.
just as a really simple example. Like the sum of the flows in all the arcs.
Oh, yeah. So I mean, you could have some flows in all the arcs. Yeah. So you could just add a global constraint to the actual graph model. So you can always get the variables of all the arcs and just add a constraint that way. There's nothing stopping you from doing that.
So it would be okay to have part of the model created by the graph, and then part of it just created separately.
Yeah, you could do that.
So I'm thinking of a slightly different type of application. So maybe could you go back to one of the early slides where you had a diagram of like multiple sort of hierarchical systems?
Oh, was it
pretty early on?
This one?
Yeah, maybe that one. So it seems like you could have some problems which are maybe highly nonlinear, maybe they're even just simulation problems at some level.
Mm-hmm.
And then at another level you have maybe some sort of scheduling problem, and then maybe you have, a larger problem across, the whole United States or something. So it's a sparse graph with different problem classes on it. And if you think about how people sometimes solve multilinear problems, so they have like a product of variables. They'll minimize with respect to the first variable, fixing the other ones. They'll minimize with respect to the second variable, fixing the other ones. So alternating minimization. Forget about global optimality. But it seems like maybe nodes could correspond to actual models or particular simulation problems or optimization problems, and you get the values maybe from that optimization or simulation, fix them in the problems that have arcs to that problem, so the sort of dependent ones, and then maybe your package has some different abstractions for algorithms that make passes over this graph and optimize the nodes and then pass on the values or something. Or you could do it completely distributed in a parallel fashion. Is that sort of...
That's what's on my roadmap. So I want to see if I can get the abstraction correct for doing that kind of workflow. So, I mean, in a sense, I think a node could be something like I just want to solve an optimization problem, and it doesn't have to be that. It could be a simulation problem, but the trick really is, I mean, how do we really manage the data that goes around? And then I would like to do it in a distributed way. So I know we saw Steve Diamond's presentation yesterday that kind of used TensorFlow to that degree, and I would like to see if some of the Julia parallel capabilities could actually come into play here.
Okay. So yeah, it seems like JuMP would go a long way because you've got nonlinear models, you've got mixed integer models, etc. But maybe not far enough, because you also might want to run simulations.
Correct.
You might want to run ODE problems, etc.
Right. So we were able to do like a simulation verification where we did like a really coarse optimization problem for a network, and then right after that we passed the results to a simulation. But I mean, it was very ad hoc, and we had to communicate through files to get it out of JuMP and get it into this PETC interface, and then get the information back and forth. I would love to have a simulation interface directly within the graph, and we could use the same structure.
So when you're developing the linkage between like an edge and a node, in most of the problems I would work on, that would just be equals. Right? There's like a variable inside of the node, which you're summing over, and then there's a variable on the edge, and you're saying, well, they're actually the same quantity. And when if you have that version and you just add all these like this variable equals this variable constraints, unless you have a very mature solving technology, it will totally destroy the convergence properties of your models. So do you have any ideas about how we might be able to deal with that?
I was thinking of some options depending on what kind of model you want to solve. So like in its most basic form, yeah, you're going to have a lot of variable duplication. I think we could get away with just maybe some simple model building strategies where we're able to do some sort of pre-solve and recognize and just give a more compact, just produce a compact optimization problem. But again, we have to be careful because, I mean, we might have one variable that's associated with multiple nodes, and I just wanted to make sure that you get the solution back in the right format that you might expect. But yeah, I have thought about that. I haven't thought about how I'm actually going to produce a more compact model.
How do you take the graph form of the model and give it to a structured solver like FIPS?
So we're having to write custom interfaces for that.
But how do you detect like the multi-level structure?
So we're going to have to define. So you'd have to define which node would represent the first stage and then the second stage. So in its most simple form, you'd have to have like a two-stage tree, and it would have to check for that.